Hello, and welcome to Backer Breaks It Down. In this episode, we are going to analyze the graph of an exponential function. So exponential functions have one of two general shapes, right? So the graph in blue here is showing an exponential growth function, okay? Growth occurs when the base of your exponential function is greater than 1. You'll notice that when we're working with an exponential growth function, it is an increasing function, so it's rising from left to right. The graph in red is showing that of an exponential decay function. Decay functions have a base that is in between 0 and 1. Notice that exponential decay functions are decreasing. Some things both of our functions have in common is their domain, all real numbers, which means they go forever to the left, so we can write negative infinity, and forever to the right, positive infinity, okay? Their range is above the x-axis, so I can say y is greater than 0, or I can say parenthesis 0, comma, infinity, because it never touches that x-axis. In fact, because it never touches the x-axis, the horizontal asymptote is the x-axis and is given by the equation y equals 0. The y-intercept of our function is the point 0, comma, a. A is the initial value of your function. This can also be found by evaluating f of 0. So when it comes to parameters, we're talking about the values of a and b. So we just got done saying that for the parameter a, this tells us where the graph is crossing the y-axis, so it is the y-intercept. The parameter b, the base, tells us whether it's growth or decay. If it's growth, our graph is going to be increasing from left to right, okay? Now, when it comes to the value of b, the greater the value of b, the steeper the graph, okay? So notice over here, you have y equals 7 to the x power, y equals 2 to the x power, and notice that the 7 to the x power graph is steeper. Okay, and it's steeper because 7 is greater than 2. Okay, now when it comes to exponential decay, right, those have a base in between 0 and 1, and these graphs decrease from left to right. When it comes to that steepness, the opposite is true, okay? So there are two exponential decay functions here. We have y equals 1/2 to the x power and y equals 3/4 to the x power. And you'll notice that the 1/2 to the x power is the steeper of the two graphs. 1/2 is smaller than 3/4. Okay, and so when it comes to exponential decay, the smaller the value of b, the more rapidly the graph falls, meaning the smaller b value has the steeper graph. Okay, now what happens if I throw this at you? Okay, so here we have our exponential function with a little something extra, that plus k. So you may recall from an earlier chapter that addition or subtraction located here indicates a vertical shift, right? So if it's plus k, it goes up. If it's minus k, it goes down. So what characteristics would change here? The domain is all real numbers, so moving the graph up or down isn't really going to change anything. The range would definitely change because the range is a y value, so it's definitely going to be affected by a vertical shift. Same with the y-intercept, same with the horizontal asymptote. In fact, this diagram here is illustrating the effect of k. So our parent function is this one here, 2 to the x power. The one in blue is 2 to the x plus 3, and the one in red is 2 to the x minus 3, right? So our original function had a horizontal asymptote of y equals 0. G of x, the blue function, has a horizontal asymptote of y equals 3. H of x, the red function, a horizontal asymptote of y equals negative 3. Okay. When it comes to their their y-intercepts, originally 2 to the x power had an x-intercept of 1 because the a value is 1. But notice that 2 to the x plus 3 has a y-intercept of 4. And 2 to the x minus 3 has a y-intercept of negative 2. Okay. So that's why when it comes to the y-intercept, you can find the y-intercept of any function by evaluating f of 0. So plug in 0 for x and calculate, right? So like this function here, if I calculate 2 to the 0 power plus 3, I'm going to get 4. Okay. When it comes to the horizontal asymptote, our parent function had a horizontal asymptote of y equals 0. The function g of x had a horizontal asymptote of y equals 3. This is equal to the vertical shift value. Okay. So if you have a function, an exponential function with a vertical shift, the line y equals k is going to be your horizontal asymptote. The horizontal asymptote is also used to describe the range of the function because it shows you how low it goes. So we can say the range of all of our functions that have this shift is equal to k comma infinity, because it goes as low as that k value and as high as infinity. When it comes to end behavior, if you look at what I have written here for exponential growth and exponential decay, you'll notice that I am using the value of k and I'm using infinity. For exponential growth, on the left, it goes towards that k value. On the right, it goes up forever. For exponential decay, on the left, it goes up forever. And on the right, it approaches that k value, right? And you'll notice like all of our functions in the graph on the right are exponential growth, like the function h of x, okay, on the left is going towards negative 3, and on the right, it's going up to infinity. So you can kind of just give yourself a visual to help you with that, right? So let's analyze some functions here. So what is the vertical intercept of the graph? So remember, I can find that vertical intercept by evaluating f of 0. So I can plug in 0 for x, or in this case t, and calculate my results. And so in this problem here, I actually get a y-intercept of 6. So when x is 0, the y-intercept is 6. Is the graph of Q increasing or decreasing? Well, given that my b value is 1.03, I know it's growth, so that means it's increasing. What is the equation of the horizontal asymptote? Well, that's y equals k. So what's k in this one? If you're like, well, there is no k. All right, I mean, so it's 0. Okay, so our horizontal asymptote here is going to be y equals 0. When it comes to our limits, we already said this is an increasing function, so imagine it looks like this. And then remember, this is where the asymptote is. So on the left of our function, it's approaching that asymptote, and that asymptote's at y equals 0. And on the right, it's going up forever to infinity. This graph can also help you with the range, okay? Like, because it's going as low as where that asymptote is, so it's going as low as 0, and it's going as high as infinity. So in problem number 3, I have the function q of t is equal to 6 times 97 hundredths to the t power plus 3. What's the vertical intercept? So once again, plug in 0 for this value here, calculate. And so when you do that, you end up with 9. Since the b value is 0.97, this function is decreasing. What is the equation of the horizontal asymptote? Well, that's y equals k, and we're talking about y equals 3. For the rest of this problem, I can create a rough sketch of this function because it's decreasing. And I know that my horizontal asymptote is that line y equals 3. And so now I can see that on the left end of my function, it's going up forever to infinity. On the right end of my function, it's getting closer to that horizontal asymptote, so 3. And then for my range, I see that it goes as low as 3 and as high as infinity. So to summarize everything here, okay, basically we had a typical exponential function with no vertical shift, and then we have one with the vertical shift, okay? No matter what, the domain is all real numbers. What changes are anything that has a y value, so the range, the y-intercept, and the horizontal asymptote. So in a typical exponential function, we have a range of 0 to infinity, a y-intercept of 0a, and a horizontal asymptote of y equals 0. In those exponential functions with that vertical shift, your range becomes k to infinity. You need to calculate your y-intercept, evaluate f of 0, plug in 0 for x, calculate. And then the horizontal asymptote is the line y equals k. And that is how Becker breaks it down.